Okay, so these are the notes for linear regression. And what I want to do is show you how to do linear regression both on Excel and how to interpret it. And I then want to show you that there are other resources out there that you can use, including the TIE 384 calculator, and I'll demonstrate that as well. Excuse me. So to understand linear regression, you need to come to terms with the fact that you have to have what we call paired data. So if you remember, when you plotted a line, you needed an x variable and you needed a y variable. So in a sense, this x variable is what we call the explanatory variable, and the y variable is what we call the response variable. Okay, so for an example, let's say that I wanted to know if the hours that you spend studying in this class predict what your overall grade should be. Okay, and so I use this information based on prior information. So let's say hypothetically X is the number of hours that you sleep, or that you study, excuse me, and the response is the grade that you receive on the test. Okay, so that's what we have right now. Okay, so hypothetical numbers, I'm going to go in descending order. Let's say somebody's crazy and they want to study 6 hours, 5.5 hours. Okay, let's go down to pipeline. 5.25 hours, 5 hours, 4 hours. Let's go with 3 hours, 2.5 hours, 2 hours, and somebody just studied an hour. Okay? I'm going to add one more. Let's go with a 0.3 of an hour. Alright, and so here are the grades that I'm going to randomly select. Let's say hypothetically we have somebody who scores, say, an 86, and then, you know, I'm trying to see if I can sort of stick to a pattern. Let's see. Okay. So if you look at the numbers, I want you to look, since this is already in descending order, you're going to look at this kind of like a pair. So you have to have the same number. So this is like 6, 86, and this would be like the equivalent of, say, 5.5, 87. Alright, and so on, right? So all of this plays down, all the way down. So you have what are called coordinate pairs. So now you can graph them on an XY axis, okay? Right, so let me get rid of this for a moment so I can do this easily. Okay, so we have two variables there. And what we're going to run is we're going to run a linear regression. So I'm also going to show you another aspect of Excel that you're not familiar with. So first thing you're going to need to do is go to File, go to Options. You're going to go to Add-ins. Okay, and under Add-ins, I want you to click on Analysis Tool Pack and then click on Go. Okay, make sure those are checked off and hit OK. Once you do that, I want to show you something really cool. I want you to go to Data. I want you to go to Data Analysis. I have to be a little patient with my computer right now. It's got like 7 applications running in the background because I don't want to waste time looking for stuff. You see here where it says Regression? I want you to click on that and hit OK. We are going to have labels. I would like a confidence interval, and I'm going to click on the top box. Notice that this says this is the Y range. So I'm going to literally highlight and hold. I click on the X range, which is my explanatory variable, and I'm going to hold and drag just as such. And I'm going to hit OK. Notice that you can also do residual plots, residuals. You can also determine if this fits the normal probability plot, which means that it can't be curved. So you can do all that with this. It's pretty cool. Alright, and so you notice that we have an output here, and we actually have our regression. See how it says explanatory? and intercept. So that's your x variable slope, and that's your intercept right there. Given the p-values are fair, I would say we're okay, although the explanatory is a little high, which tells me that the model is not a great fit. Now, here's another thing I want you to consider. If I go back to the data, and I say, okay, equals SLOP, and I double click on the slope, notice how it asks me for the y's and the x's first. So the y's first, then comma, and then it asks me for x's. And it has to be even, so you go over, start again, hit enter. Notice the number. 1.43, this is the slope, right? Okay, I want you to go back to this page. What do you notice? See that value right there? If I want the intercept, so if I want the intercept, I'm going to do the same thing. I'm going to come over here, I'm going to say equals int. I'm going to double click on intercept. It's asking you for the y's first. Notice I'm not using the labels. Comma, and here are the x's. Enter. Notice that number, 74.30859. Look at this number, 74.30859. Okay, and so what you've done here is you found two ways to make a determination as to whether or not this is a good fit. First of all, look at the R value. This is the correlation coefficient here. Very low, telling me that there is almost no association between these variables. We would only have we do have a positive but very weak association between the two. So it's kind of like the SAT, where you could study, but no matter, there comes a point where it's like you know it or you don't, you know? Alright, and so this is the coefficient of determination. And this tells you the percent of variability in the model. So in this case, we have a 5.7% of the variability present in the model can be explained by the explanatory variable, which says basically how much you study has no impact on your grade in this case. This standard error tells you how much, this is like your margin of error, it tells you how much error there is in the model. That's a 12.7, that's high. Okay? Now you remember correlation coefficient, which we talked about previously. In this case, the interpretation of this is we have a positive and weak association between x and y, which in this case it's the number of hours one studies and the grade received. Alright, so that's the interpretation of the correlation coefficient. If you want to interpret the coefficient of determination, you would say 5.7%, because you always round it to at least one decimal place, of the variation. I want to have caps. Of the variability or variation present in the model can be explained by variability present in x, the explanatory variable. So in other words, again, what that basically says is go ahead and study all you want. It's not going to make a difference. Your score already has been determined. Okay, now as far as this, I want you to understand this part here. You see that significance at 0.5? Remember the p greater than alpha, p less than alpha argument? So if p is less than alpha, and we're assuming alpha at 0.05, notice that we have 95%, right? So if in this case the p-value is not less than alpha, then we fail to reject the null, that there's no difference, right? Or no change, right, in this case. So there's our significance value. That's your p-value. 0.5 is not less than 0.05. It's greater than. So we would fail to reject an all, and in this case, if I fail to reject an all, there is no difference in the amount of hours you study versus the score received on a test. The same thing we talked about up here. Okay? Now, let me show you the same question modeled here. Alright, and so I also want to talk to you about a residual, but let me do this first so I can show you a couple of tricks of the trade. So for this test, you would do stat test, you would go up to line reg t-test, which is right there. Okay? Notice it's asking you for list 1, list 2. The frequency, you always want this, in this case, to be not equal to, because we don't want it to be equal to, and then we would calculate. So let's go into stat edit. I need to drop in those numbers, so let me clear and delete. Come over here, I'm going to clear, and I'm going to enter. Okay, so let's go. Let me just put the numbers in real quick. Accuracy in this part of the math is crucial, because if you're not accurate, you're going to get numbers that don't make sense. Alright, and I'll come over here and go 86, 97, 98, 65, 67, 87, 76, 78, 60, and 90. Okay, see how they're paired? They're all together, little pairs, right? So let's go back to stat test, and we'll go to line reg t-test. I always come up from the bottom because it's so much easier. And I want to just simply calculate at this point. Alright, so you see how this is giving you this equation? It says y equals a plus bx. A is your intercept. Notice it's 74.308588. Same thing we got here, right? And then if you scroll down with the arrow key, you will notice that you have x. X is there. Test. I must have hit a button or something. Line reg t-test. All the way down to calculate, hit enter. Okay, so let me just scroll down. There you go. There's your slope, 1.47, 36, 36, right there. You notice the standard error is 12.7, which I said was very high. There's your correlation coefficient, and there's your coefficient of determination, both that you've also obtained in the regression analysis. Now, I have one more toy for you, in case you don't want to use either of these tools. I'm giving you lots of options. Alcula is an online calculator that will do all of this for you and more. So you go to alcula.com, online calculators, and if you have your data already set up, notice that I'm going to go to linear regression calculator. Right, and I gotta partition this over. Okay, notice that I'm going to grab both of these columns together, go control copy. I'm going to come over here and I'm going to do control paste, and I'm going to hit submit data. Look familiar? You see here, this is the equation itself. That's the whole equation. Notice that the slope of 1.4736 goes with the x, so you substitute in a value x to determine or predict the value of what would be, you know. So you notice when you look at the scatter plot, see how you have the y and the x. There is no distinctive grade value there. Okay, so I gave you a nice model in this case to make your brain think. Since we have such a low correlation, we would actually use descriptors, meaning like the mean, median, mode. And if I were to adapt this to actually compute the data differently, so I'm going to change the data for a minute. I'm going to do a test where your amount of hours studied will pay off. So basically, it's going to be a perfect linear, and notice how the numbers are changing because I used Excel to compute this. and I use the actual cell values. Let's see here. I'm trying to go in descending order and not swerve too much from here. Alright, and let's do 76. Actually, let's make this one low. Let's make it a 60. Okay, notice the value there? Okay, so let's do this again with Alcula. Let's see what kind of scatter plot we get. Oh, let me show you the scatter plot instead this time with Excel, since you already saw it that way. Right, so, oops, I forgot to highlight the data. Alright, so there's my data. All I did was highlight it and then go to scatter plot. Oh, and there you are. See how perfectly, or almost perfectly linear this is? So this is nice. So if I do, let's do this. I'm going to highlight all of this now. Control copy. Let's go to Alcula, because I think I need to show you one in Alcula. And then we'll do another regression. Okay, so let's say hypothetically you want to reset the data. Just reset. Go back in, control copy, submit the data. I should. Let's reset. Oh, I'm sorry, I grabbed the titles, so don't grab the titles. Okay, so here we are. Let's go back up. I have to get rid of this because it doesn't like the letters. And you should be able to get. Let me just reset it. Alright, so no titles. Look at how pretty that one is. And I also want you to notice how strong the correlation coefficient is. So if you look at the correlation coefficient link right here, just click on it. It's going to tell you in nice bold letters that that R value is 0.94. That's pretty. So the amount of hours you study does affect your grade in this case. Okay? It also can do the box plot for you, given the data. It could do all sorts of information. And it also will give you the option of, now this is paired data. You would only want singular data, so I'm not going to do that with this. Okay, so let's look at one last thing here for linear regression. And so let's do data. Let's go to data analysis, and we want regression. And this time, I'm actually going to leave it the way it is. Hit OK. And look at that. I want you to notice the p-values here. See how those are truncated? You see how that's a negative 0.05 at the end, E? Negative 0.05, so that means that's 0.00000521. So it's good. So it's a good model. Also, look at the R value, 94.94 for the correlation. So you have a strong and positive association between the two, indicating that the number of hours you study will determine the grade received. Here's your R square. So 88% of the variability present in the model can be explained by the explanatory variable X. And you can see that. See, the standard error is only 4.179, much smaller, so there's less error. The other thing to consider is this. Look at the significance level. That's 5.21e to the negative 0.05, which is telling me that the p-value is very small compared to an alpha of 0.05, so we would reject the null. There is obviously a difference between the number of hours studied in this case and the grade you receive, so there is not. So this would make this a very powerful explanation. So this is also, by the way, an ANOVA. This is how regression and ANOVA tie together. So if you notice, you get the same values. Look at the intercept. Look at the explanatory variable. If I go back here, look at the intercept. Look at the explanatory variable slope. Same difference, right? And so that means that there is a line that's running straight through here that can help us predict the value. So let me talk to you about one last thing and I'll stop. The residual. Notice that you have the option of having residual. And the residual, by definition, is the actual value minus the predicted value. The predicted value is what you're going to compute here. Okay, so let's pretend this is the actual. And here's your predicted. So the actual value, let's go with a 6. Let's start with the 6, right? The predicted is equal to the intercept plus, and it's plus because the slope is also positive. So in this case, I'm substituting in 6. And notice that that difference for the residual is equal to the actual minus the predicted. And the actual value, I'm sorry, there should be 100. So the difference between the actual minus the predicted is your residual, which is this little bit right here. And you could do that for all of these now that you have the formula here. And so we would simply, recopy these numbers down here. So because that's fixed, so control copy, control paste, and my predicted formula sits right here. Right, I'll just copy all that. Now, only reason it's giving me zeros at this moment. All right, see here. So, in the formula, you also need to control this number by putting a dollar sign, because basically you're using the same formula for the slope and for the intercept. And the way Excel works, it for example, the next number that it did would have been D4 instead of D3, and D5 instead of D4. So when you put the parentheses, it makes it go back to that all the time. So now watch, when I do, notice if I click here, you see how that went D4, D5? And if I click here, you see how that's D5, D6? Now, once I put that dollar sign here and I drag that formula down, it's going to always use, and I'll show you, it's going to always use the same value. See? It always goes back to the same respectively. So you can input various values and determine. So if I change that to a 7, what happens? What happens if instead I study, say, 3 hours? Right, and so on. So you can see the different residual values. Okay. So that's what the residual is. It's the actual value that you observed minus what you actually would predict based on the model. All right. Well, I hope this has helped you. And one more thing. The slope. When you interpret the slope, this is an increase because it's positive. If that were negative, it would be a decrease. So this line would be going down instead of up, right? The other thing to consider is when we interpret the slope, we would say that for every increase, so basically for every increase of 1 unit in predicted, in x, the explanatory variable, there's an increase of 5.4546 in the intercept, or in the predicted y. Okay, so the model itself would be predicted y, which looks like this. It's basically y hat is equal to that intercept value, which is in our case, let me just write it out. So it would be 66.55 plus the slope 5.45. Let's leave it at that, and then x. So it's kind of like times x. That's your model, right? So for every increase of 1 unit in x, there's an increase in predicted y by that amount. When x is 0, notice that when x is 0, that's going to cancel that out, and that's what your y-intercept represents. So if nothing exists, that's your value. Okay? That's pretty much everything. Hope this was helpful.